Your your screen is being shared and the recording is on. So over to
Okay.
you. All the best.
Okay. Good evening, everyone. Today I'm going to take a class on the topic beams. So first of all, introduction. We all know that beam is a structural member which is used for bearing the loads coming on it, and also it is typically used for resisting the vertical loads coming and also the shear force and bending moment. Then this mode of deflection of the beam is mainly by bending. These beams can be classified based on the number of support conditions, profile, length, and the material. So first of all, based on the types of the beams. According to end support, first it is classified as simply supported beam. So, like showing in this figure, simply supported beam is supported at both the ends, and one end can be hinged and other can be roller, or both ends can be hinged or both ends can be roller. Also, this support allows horizontal movement of the beam. Also, it undergoes shear stress and bending moment. Next is the continuous beam. It is similar to simply supported. Its variation is that there is more than two support in this beam. Also, both the ends can be hinged or it can be roller. One or more supports are more than one support is there in the mid midspan. Also, it is used in long concrete bridges where the length of the bridge is too large. Next is the overhanging beam. Overhanging beam is the combination of both simply supported and the cantilever portion. Uh, in one case, sometimes it can be one side overhanging, or sometimes it can be both side be overhanging. It is supported by roller support at both ends or hinge support. Next, also it has the similar properties of that of simply supported and cantilever beam. Next is cantilever beam. Cantilever beam is a structural member in which one end is fixed and other end is free. Mostly, this type is used in trusses, bridges, and other structural members. Also, it carries the load. It carries the load over the entire span, and also it undergoes shear stress and bending moment. Next is the fixed beam. It is fixed at both the ends, and it does not allow vertical movement or rotation. It is deflects under shear stress, and no moment is produced in this. Next is types of reinforcement in beam. There are two types of reinforcements in this beam. The reinforcement provided top and bottom, that is in the tension and compression phase, it is known as a longitudinal reinforcement. And the reinforcement which is provided vertically, that is in this bend up like portion, it is known as the shear reinforcement. Next is the cover. The minimum cover we should provide should not be less than the larger diameter of the bar or 25 mm. Next is the development length. Development length is the minimum length of the bar which is embedded into the concrete in order to develop the full strength. This third portion is known as the development length. It is also known as anchorage length in case of axial tension or axial compression. So it helps to transfer the stress or load to the beam, to column smoothly. So the development length we provide for the beams are 50 times the diameter of the bar. So for example, in case of 12 diameter bar, we provide 50 into 12, that is 600 mm. So we provide 600 mm provide in this portion. Next is the code specification. That is IS 456 2000 specification. First of all, the minimum tensile reinforcement, that is minimum area of tensile reinforcement should be satisfy this equation, that is AS by BD is equal to 0.85 by F5. In this, AS is the minimum area, B is the breadth, D is the effective depth, and the maximum reinforcement should not be greater than the 4 times the cross-sectional area. Next is the side face reinforcement. In the case of the beam which depth is greater than 750 mm, we should provide side face reinforcement on the both faces, and its area should be less than 0.1 percentage, and it should be distributed equally on both the faces with the spacing not greater than 300 mm or web thickness. Next is the maximum spacing of the shear reinforcement should not be greater than 0.75 times the effective depth. Also, it should not be exceed 300 mm. Next is the minimum shear reinforcement. Minimum shear reinforcement provided should satisfy this equation. That is ASB by BSB should not be greater than 0.4 by 0.87 SY. ASB is the cross-section area of the stirrup provided. SB is the stirrup spacing. V is the breadth. In our case, the ASB, that is the shear reinforcement provided for 8 bar. There is an equation that is 32,000 pi by provided area, and for 10 bar, we provide an equation that is 60,000 pi by area. Thank you. So next, the detailing part in Xbuild will be taken by Anjana.
Good evening, all. I will share the screen. Okay, first we need to open E tabs. Then we need to analyze analyze the model. First we need to analyze the model. We'll take something. Okay. Then we need to do concrete design. Then we need to select the respective floor to which we need to do the detailing. For that, from here, we need to select here. Now today, we will see the detailing of a plinth beam. So select ground floor. Then from here, we need to select the longitudinal reinforcement. Then we need to select this floor. Then take Ads Pro. First, we need to open a AutoCAD file. While doing this, only one AutoCAD file need to be open. Otherwise, it will show some error. Open an AutoCAD file and take Ads Pro. Select this beam tab. Here, we need to select this icon using E tabs. Then right click here and select load from E tabs model. Then we need to convert this data. For that, click here, convert data. Yes, converted. Then click on this drawing CAD. Then open. And click any click on a point. Beam detailing is being generated in AutoCAD file automatically from Ads Pro. Now we got all the detailing. Now we need the layout for these respective beams. For that, take Ads Pro. Then click on Draw Layout in CAD option. Then Draw. Open it tabs. Sorry, AutoCAD and click anywhere. Layout is drawn. Okay. This is how we will generate detailing from AutoCAD. Okay. Now I will take another file. So already. Okay. This is already existing detailing. I will show detailing using this file. This is the layout, and we will name this beam in an order that is we will name from vertical beams first, that is B1, B2, B3 and B4. Then or after these vertical beams we will name those horizontal beams. That's the order for naming. Uh, okay. Now for that, we will select on beam. Let's take B16 and B17. Okay, B16 and B17. Okay. Now we will take E tabs. Uh, we can open longitudinal reinforcement details here, and in this window we can open shear reinforcement. Okay. This is a beam that we are now discussing, B16 and 17 in detail. That this one. Okay. This longitudinal reinforcement required for to resist the moment acting on these beams is at support 427 mm square steel is required, and at this is the J end, and this is, let us consider this as J end, and this end as sorry, I end, and this end as J end of the beam. At the I end, the top reinforcement required is 427 mm square, and at J end 510 mm square. At the middle portion, we require only 185 mm square. For beam, the longitudinal reinforcement, the bars bars we usually use are 12 mm dia bar, then 16, 20, and 25. The area of a bar, as we all know, the area of a bar we can determine by pi r square by 4. Using that, we know that the area of a 12 mm dia bar is 113, and minimum number of bar required in a beam is 4. That is 2 at bottom and 2 at top. So at top we need at least 2 2 number bars. So here uh, two numbers of bar. 12 mm 12 mm dia bars have an AST of 113. For one 12 mm dia bar, the area is 113. Uh, for 2 it is 226, and for 3 it is 339. Likewise, we can calculate the area. Here at these supports, one is 427, and at this end 510. The area for 2 minimum reinforcement, that is 2 tall, we have 226. It is sufficient at this center portion, but not sufficient at these ends. So we need to provide extra reinforcement at both ends. Extra reinforcement, that means 427 minus 226, that is 201. Hence, we can provide two two numbers of 12 mm dia bars at this end, and here also two numbers of 12 mm dia bars will be sufficient. Now, that's not shown here. Main bar is 2 tall, and at these supports we provided extra bars, that is 2 tall extra, two numbers of 12 mm dia, and here also two numbers of 12 mm dia bar. Now we need to calculate this length, that is to which distance these extra bars to be provided. For that, we need to take the E tabs, then do moment. Check the moment. For that, we consider this envelope combination, and it's changed to maximum minima. Then component is moment 33. Now apply. Okay. This is B. Okay. Now we can find this distance. How much distance we need to provide this extra bar at this I end. For that, open E tabs. Now in this end, then scroll for the maximum value at I end. Moment value at I end. Here it is 60. That corresponding shear value is 59, and to calculate the torsion, that is 0. Okay, now take and probe. and scroll then this beam design here, and we need to provide the width and depth of the beam. That is 200 by 400. Here 200 by 400, and nominal cover for beam is 30, and we need to provide these inputs that we got from ETAP, that is moment was 60 and shear force. Moment was 60 and shear force was 59 and torsion was 0. That is these values, maximum moment at this end and corresponding shear. That is for top, we will consider this negative moment. Okay, now and here then we have to provide this compressive reinforcement, that the main bar we provided are 2 numbers of 12 mm dia, tensile also 12 mm. Then execute. We got 4 numbers, but we only provide 2 numbers of 12 mm dia bar. So then we need to make this number of bars as 2. For that we will reduce the moment. Let's 45 and execute. Now 3. Reduced moment reduced to 30. We got 2 numbers. Okay. These two numbers of bars will resist only moment up to 30 kilonewton meter. So then open 8 tabs. Select. We need to scroll. We can scroll like this and then scroll and stop at which moment shows 30. Okay, moment shows 30. That means from I end, this is the I end, from I end at a distance of 0.6 meter, 0.6 meter, we need to provide extra bar. That is 212 extra bar. About 0.6 meter, but for we also 0.6 plus LED, we should provide that. We should provide this value plus LED. Okay, plus LED. LED for 12 mm dia bars is 50D, that is 600. Here it is 0.65, that means 650. 650 plus 600 means 1250. And we rounded it to 1300 and provided 2 numbers of 12 mm dia bars extras at 1300 distance. Now we need to calculate this length. For that, again open ETABS, scroll these values to the J end, and here the maximum moment is 70. 70, let's take it as 71, stay 70, and corresponding moment shear is 63. Torsion is here also 0.4. Open adds pro with the moment of 70. Shear 63. Torsion 0. 0.4. Here also total, then execute. Here we got 6 number bars. Then we only need 2 numbers. For that again we will reduce this moment. Then it became 4, 30. Okay, we got 2. So we need to calculate the length up for this 30 moment. Open ETABS. Here we need to scroll for moment 30. Okay, 30. That means 4.93. That means these values are from this end. From this end, 4.93. We need this. We need the distance from this end, this J end. For that, the total length is 5.86. Means 5.86 minus 4.93. That is 0.93. 0.93 plus LD. 0.93 plus LD. That is 930 plus LED for 12 mm die bar is 50D 600. 600. That is 1530. Rounded to 1600. That's how we will provide uh, the extra bar. Yeah, okay. So that is 16. Then now we can look for this 17. B17. Okay. For B17, we have 402 as at the I end and 272 at the J end. The main reinforcement we provide is two numbers of 12 mm diabar, that is 226. It is sufficient at the middle span, but not at the supports. Here we need to provide 402 minus 226. That is 127. That is two numbers of 12 mm diabar. Here we need only one number of 12 mm diabar. That is 113 is only required here. Here also we will take the moment. That is 56. Corresponding here is 56. Torsion as 1. Moment 56. Here 56 and torsion 1. Execute. 4. We can reduce the moment. Now it's 3. 30. Okay, moment. We need the length for moment 30. Open meters. For moment 30. Okay, that is 2 point. Okay, 0.7. Next take 0.7 plus LED, that is 1.3. That's what provided here. 1300. Similarly, at this J end, here the moment is scroll to this J end. Here the moment is 38 and corresponding shear is 48. Torsion 1. Take as probe. Moment 38. Shear 48. 3 number we need to reduce to 2 numbers. Okay, here also 30. Take as probe for heat taps. Scroll for 30. That is 2.9. Here also we need to calculate the distance from here, from the JN. 3.2 minus 2.9. That is we will get 0.4, 4.4 plus LD 0.6. That is 1 meter. Okay, so here we provide 1000 mm. This at 1000 distance one number 12 mm dia extra bar. That's how we provide extra bar. And for this bottom reinforcement, these was the bottom reinforcement. Here we need, here we provide three numbers of 12 mm diameter, that is 339. So it will be sufficient. So no extra reinforcement is required here. That's how we do this longitudinal reinforcement detailing. Now we need to calculate, we need to detail this shear reinforcement. For that, we need to take tabs, select shear reinforcement, apply, okay. These are the required required area of steel. It will resist shear. It will resist shear. Always we will provide maximum shear reinforcement at the supports and at the supports. Here, maximum reinforcement at support. The shear reinforcement, that is we 8 mm and 10 mm dia bars are usually used for shear reinforcement. Shear reinforcement, we will provide more reinforcement at the supports. At the minimum spacing for reinforcement reinforcement is 200 mm and the maximum is 100 mm. 100 mm. Here we require 626 mm square reinforcement at the supports. It calculate the spacing. It calculate the spacing. We know the equation that is 1000 by number of reinforcement. From that we have derived two equations, that is 32,000 1000 pi by AST for 8 mm dia stirrups and 5000 pi by AST for 10 mm dia stirrups. From that equation, up to 1005 mm square AST, we can provide 8 mm dia shear reinforcement at 100 mm spacing. If the shear reinforcement required exceeds that, we will go for 10 mm dia stirrups. Now, here we require only 8 mm dia stirrups. At the supports, we will provide 8 mm dia stirrups at minimum spacing, that is 100 mm spacing at all supports. That's shown here at these supports. And up to which length we need to provide these these support shear reinforcement we will determine by the equation, that is 2D. 2 times the depth of beam. Here the depth of the beam is 400. That means 2 into 400, 800. From the supports, the shear reinforcement starts at 50 at 50 offset from the support. From the here, at 800 distance, we will provide shear reinforcement at 800, and here also 800 at all supports we will provide 800. At the midspan, we need to calculate the spacing at which we need to provide shear reinforcement. For that, here we have 451 mm square required. We will put this in the equation 32,000 pi by AST. It's 32,000 pi by AST. Here AST required is 452. That is 222. That means we need to provide. That means we need to provide 8 mm dia stirrups at 200 mm spacing, because the maximum spacing we provided is 200 mm. Okay, here it is here it is 5. The required AST is 510. For that, we will again put it in the equation 32,000 pi by 510. Then we got 197. So here we provide rounded to 180. 8 at 180 spacing, we provided the stirrups. That's how we provide longitudinal reinforcement and shear reinforcement using ADS Pro and ETABS. Okay, that's all. Do anyone have any doubts or questions? Hello? Hello?
Hello?
Do anyone have any doubt? Hello?
Okay, then we can end this section. Okay, thank you, Anjana.
thank you. Sure. Hello. Okay, thank you. We can end the session.